What specific problem does your proposed method of model merging aim to address, particularly regarding large-scale models, and what gap in existing research does it fill?
Our proposed method of model merging aims to address the scalability and effectiveness of merging large-scale models, specifically those with parameters exceeding 7 billion. Existing research has primarily focused on small-scale models and limited merging scenarios, often failing to explore how factors like model size, base model quality, and the number of expert models influence both held-in performance and zero-shot generalization. By systematically evaluating the merging of models up to 64 billion parameters and utilizing both pre-trained and instruction-tuned base models, our work fills the gap in understanding the interplay of these factors at scale. We demonstrate that larger models facilitate easier merging and that using strong instruction-tuned models significantly enhances the performance of the merged models. This comprehensive study provides insights into the potential of model merging for creating highly generalizable language models, which has been largely overlooked in prior research.
How does the proposed model merging algorithm work? Please illustrate it step by step, including how different merging techniques like averaging and task arithmetic are executed in practice.
The proposed model merging algorithm combines multiple expert models to create a unified model, leveraging various techniques such as averaging and task arithmetic. In the averaging method, the weights of the expert models are simply averaged together, which can be mathematically expressed as theta_m equals frac1, n sum_i equals 1 caret n theta_i, where theta_i represents the weights of each expert model. In contrast, task arithmetic involves calculating task-specific vectors by subtracting the base model weights from the expert model weights, denoted as tau_i equals theta_i theta_base. The merged model is then constructed by combining the base model weights with a scaled sum of these task vectors, formally represented as theta_m equals theta_base plus lambda sum_i equals 1 caret n tau_i, where lambda is a scaling hyperparameter. Additionally, the merging process can be enhanced by using techniques like ties and dare ties, which address challenges such as noise accumulation and parameter conflicts among expert models. Ties merging first trims low-magnitude values from task vectors and resolves sign conflicts before averaging the remaining parameters. Dare ties further incorporates a dropout-like pruning stage to reduce noise in task vectors before merging. Each of these methods aims to improve the robustness and performance of the final merged model, particularly in zero-shot generalization tasks.
Can you provide a specific example that illustrates the merging process of two expert models using your method? Walk through the steps of merging these models with hypothetical parameters.
To illustrate the merging process of two expert models using the task arithmetic method, let's consider two hypothetical expert models, theta_1 and theta_2, derived from a base model, theta_text_base, with parameters of size 64b. First, we calculate the task vectors for each expert model. Tau_1 equals theta_1 theta_text_base, and tau_2 equals theta_2 theta_text_base. Next, we introduce a scaling hyperparameter, lambda, to control the contribution of these task vectors to the final merged model. The merged model parameters are then computed as theta_m equals theta_text_base plus lambda, tau_1 plus tau_2. For example, if lambda equals 0, 5 tau_1 and tau_2 are averaged and added back to theta_text_base to produce the final merged model, theta_m. This process effectively combines the specialized knowledge from both expert models, while retaining the foundational capabilities of the base model.
What are the empirical or theoretical benefits of using your model merging approach compared to existing methods? How do these benefits manifest in different model sizes or configurations?
The empirical benefits of our model merging approach, particularly when using instruction-tuned base models, are evident in improved performance across various configurations. Our experiments demonstrate that merging models derived from instruction-tuned bases consistently outperforms those from pre-trained models, enhancing both held-in and zero-shot generalization performance. Additionally, we found that larger models facilitate easier merging, allowing for the effective combination of more expert models without performance loss. This scalability is crucial as it enables the merged model to match or exceed the performance of strong multitask training baselines, particularly when leveraging larger model sizes, up to 64B parameters. Overall, our findings indicate that the choice of base model quality, model size, and the number of constituent models significantly influences the effectiveness of merging, showcasing the advantages of our approach in creating highly generalizable language models.
How did you validate your experimental findings on model merging? What metrics and datasets were employed, and how do these validation strategies support the reliability of your results?
To validate our experimental findings on model merging, we employed a comprehensive evaluation strategy that included both held-in and held-out tasks. We utilized the T0 mixture dataset, which comprises 8 held-in task categories and 4 held-out task categories, selecting 2 datasets from each category to ensure a robust evaluation while minimizing costs. The performance of the merged models was assessed using normalized performance metrics, where held-in tasks were normalized against the corresponding expert model's performance and held-out tasks were normalized relative to the base model's performance. This normalization allowed us to create a unitless metric that facilitates comparison across different datasets and models. Additionally, we conducted approximately 9,000 model evaluations across various experimental setups, ensuring that our findings are reliable and generalizable across different model sizes, merging methods, and constituent models.
What are some inherent limitations or potential drawbacks of your model merging approach, especially when scaling to very large models? How might these affect its applicability or performance in real-world scenarios?
One inherent limitation of our model merging approach, particularly when scaling to very large models, is the potential for noise accumulation during the fine-tuning of expert models, which can hinder the merging process. Additionally, different expert models may modify the same parameters in conflicting ways, leading to interference that negatively impacts the merged model's performance. Our study also highlights that while larger models facilitate easier merging, the complexity of managing multiple expert models increases, which could complicate the merging process and affect performance consistency. Furthermore, existing studies on model merging have primarily focused on smaller models, leaving a gap in understanding how these limitations manifest at larger scales. These factors could restrict the practical applicability of model merging in real-world scenarios, where robustness and adaptability to diverse tasks are crucial.